and I shut it all down and do it again the next day. So
wonderful. Well, Drew, thank you, man. So let me go to Ernesto. Ernesto.
Yes, hello, hi everybody.
Hey, yeah, and you had an ultra-fast neutron concept. Do you want to do a
Yes.
screen share and show them you could show them your schematics and
how do I switch between screen one? Yeah. Can you see it?
there we go. Yeah.
Okay. Well, I have very basic physics, but I think that this is a functional concept. It is basically based on the principle that if you eject mass in one direction, you will get thrust in the other direction. And my original idea was that if you have a piece of radioactive material in space, the natural decay of the atoms will generate a thrust omnidirectionally, given that the direction of the particles emitted in the decay is random. So if you could somehow control the natural decay of radioactive materials, you could probably get some thrust in one direction. But this design more or less uses the same principle, but instead tries to use the energy that neutrons have when there is a sustained nuclear reaction, a fission nuclear reaction. So the concept more or less is to have a piece of, to have a sustained reaction in the center of the device as the source of thrust, and then surround it with some kind, I don't know the material science for this, and I believe that there are problems with the high temperature and the stability of the material that could do this work. But basically, if you have a sustained nuclear reaction, and you put a concave shape around it, like a parabola, like a parabol, the neutrons that are escaping in the backward direction will generate thrust forward, and the neutrons that are escaping in the forward direction will bounce back on the surface of the shield or the cone, and you will get forward motion. That is more or less basically the concept. I don't know if I'm missing something, because this is a very basic functioning principle. I have read that normally on a sustained nuclear reaction, you can get up to 50,000 neutrons with speeds of up to 50,000 kilometers per second. That's why I'm assuming that could be the maximum potential speed of the vehicle. And that I didn't put, I'm not using the presentation, but more or less this is it. Using the fusion, like the fission process, like I said, trying to redirect the neutrons in a direction that is favorable that facilitates the motion in the space, following the trajectory that we want to follow, whatever. Obviously, this will provide very little acceleration, but it's a sustained impulse for thousands of years, as long as the reaction lasts, the sustained reaction lasts. And I think it could be useful for probes and things like the Voyager probe and interstellar instruments or whatever. I don't know. My main interest is to see if I'm missing something here, if this is functional, if there is material science that can make this possible. Listening to the previous presentation, I realized that if there is a way, using whatever methods you guys are using, like sound waves or the combination of sound waves and electromagnetic signals, to orient to align the atoms in a radioactive material, And this is absolutely, I know that at the moment this is out of the physics that we know, but if we can predict when and in which direction a neutron, a decaying particle from a decaying radioactive material will escape, and if somehow you can orient the atoms in a way in which that decay will have the direction that you want. I mean, if you can orient the spinning of the atoms, and if for some reason you can orient also how the particles are going to escape, you will also generate some thrust if you can somehow predict the escaping trajectory of the decaying particles. But yeah, that is far too scientific for the moment, I believe, out of our reach. But I think that this concept of having like a neutron absorbing or a neutron reflecting material surrounding a sustained core, it will generate thrust. So I'm open to questions, and if you guys see something that I'm missing, please let me know. That's more or less that's more or less it.
Awesome. Thank you, Ernesto.
Sure.
Let me see. Does anybody have questions for him?
I was gonna add, wait, did you say the neutrons would have a speed of, was it like tens of thousands of, was it meters?
50,000 is what I've read.
Kilometers per second. So that's for the neutrons. And then have you considered how massive, and just in terms of momentum conservation, have you thought about, how big the craft would be and compared that to the mass of the neutrons themselves?
No,
I
not
think-
really. I haven't done any math. I'm only working with the no numbers, just basic principles,
For sure.
But I haven't. I don't have the math and the technical knowledge as to plug the values into the formulas and do all that work. I'm basically working here with high school physics. I
Oh
dropped
yeah.
high school.
I'm just talking about high school physics as well. So I mean, the mass of the neutron is going to be pretty small, right?
But you should have a lot, right?
Yeah. So I mean, that's the thing to think about. Yeah, I mean, it's something that you could think about.
The idea is you already have launched the probe or the device using a chemical rocket or another medium, So this already you're probably launching it already with the escape velocity that is higher than the required to leave the solar system, So this is just to add a little. It's like a solar cell that you launch first, and then if you have just a tiny little bit of thrust for 20,000 years, you do gain acceleration, In my opinion, that's a question that I'm asking. So say that you launch this with a chemical rocket and you already have 20 kilometers per second. I don't know how fast a chemical rocket can launch something out of the solar system. But if you have, say, 20 kilometers per second, and you are emitting neutrons at 50,000 kilometers per second, I'm pretty sure that you gain some momentum forward,
Yeah, it's still going to obey the Rocky equation, though.
Yeah.
Meaning
So
that it
you
will
can-
gain
you can-
acceleration as in the same measure that it loses masses.
Yes. So yeah, you can calculate it using the rocket equation.
Okay. I can try maybe someone in a forum to help me do that. I'm never sure about doing my math right. So maybe I can try to do it and bring it here and you guys can correct it if it's wrong.
Well,
Yeah,
I
give
would
it a
say
shot.
Well, and then Daniel, I think you had a question or comment also.
So you're using neutrons, obviously. You said you're going to use a reflector like graphene or probably or beryllium would actually be a better reflector. How are you dealing with the reflector decaying over time as it gets bombarded with the neutrons?
That's the material
How thick
science
does
I
it need
don't
to
have.
be?
Yeah, those are probably the engineering problems that I would need somebody to do research, or I could do it myself. I'm just presenting it here, trying to find precisely those questions, But it's such a simple mechanism that it should be so complicated to find the weak spots, Because it's basically a problem of material science and basic physics. If you really can absorb neutrons and then generate a differential of thrust, then I think this will work.
Yeah, one of the things I'm wondering too is if you're using a nuclear substance, nuclear material, maybe there's a way to double use that, right? To generate heat for like a Stirling cycle reactor. I mean, because that's one of the things they do for a lot of satellites. They're using nuclear materials. So maybe
Mm.
there's a way
They
to
have,
double.
so a lot of those, they're radioisotope thermoelectric generators that they're using in like the deep space stuff. They're not heating up water to do like a steam cycle. They're not very efficient.
Mm. I would guess that as simple as possible because you really want to keep the mass low to maximize any thrust that you get from such a small impulse, you know? That would be my initial thought.
I'm just seeing a lot of weight here to deal with the shielding for the payload equipment.
Mm. Yeah, well, I don't. It's just a principle, you know. It's probably not even feasible, or not even practical from an engineering point. My interest is finding out more if it would actually work, but I don't know.
You'd need to calculate the specific impulse that you'd be expecting to get.
Mm-hmm. Yeah, that was my thought, more or less. Which should be infinite. I mean, infinitesimally more small. I would expect. But somehow there should be an equivalence. If you say say that you have the power that is generated by a nuclear core of like a small nuclear reactor, it's like 300 megawatts and it lasts for 5 years, I think, or 20 years, I think. So if you get like 10% of that power, if you launch like a small nuclear reactor with that shielding on front, and you gain like just a 1% differential between all the energy, and you're able to capture just 1% of those 300 megawatts for 20 years. I think it's substantial energy, I would think. Right? Hello?
Wonder what the I
Yeah,
wonder what
sorry
the
about that.
mass of a nuclear reactor is.
Yeah, well.
I'm
But
sitting here thinking,
is my reasoning correct, or am I missing something there?
I mean,
The
like
prob-
in terms
the
of a
problem-
Newtonian reaction, you're still you're throwing some kind of mass out the back, so you should expect some kind of thrust to go forward. It's going to be hard to calculate how efficient this is going to be without knowing, like David said, how massive is the reactor, how much shielding do we have to go in it, like I see what you're going with.
Yeah, in theory, you know, you could get some
Yeah,
thrust.
it's a very theoretical device. It's very
Yeah, in theory, it could get thrust, but
probably
yeah,
even it might be
Might
the
be
case
small.
that even the solar wind has a higher influence in the system than the actual thrust. But just a principle. I'm interested more in if the reasoning behind the design is right.
The problem is you have to make sure that you're reflecting the neutrons away. Otherwise, it really doesn't matter because you're going to fry your payload. The electronics will be degraded from the neutron flux.
No,
So-
I'm not even trying. The idea behind it is not even trying to make it practical to measure anything or send any payload. Just to know if, in the case that we should launch something like that, would it actually accelerate forward? It's just my question. I don't think it's practical, probably.
I
The
think
only
it
way
probably
is
would
to-
accelerate. Go ahead.
You'd have to make sure that whatever magical material this is actually reflecting the neutrons, that you
Well,
have it
it
going
could
in a
absorb
preferential direction.
And if I believe that an absorbing material would work as well, right? Because if you are emitting neutrons omnidirectionally, and one neutrons are escaping in one direction and the other neutrons are being absorbed in a shield, those neutrons are communicating their forward impulse to the front of the chip and contributing to a thrust as well.
So I think you could technically get some kind of thrust in this vacuum. Now, my concern with it is with the amount of material and resources that it would have to go into it to get this to work, could you have gotten a better product for the
Yeah,
same?
most likely, yes, for sure. Good questions.
I'll let someone else go now.
What
Wow.
what occurred to me, what made me think of is now your design is throwing the neutrons out the back, but now you've shown that you can move these neutrons at like, you know, roughly a little less than half the speed of light. We know that like acceleration of matter creates gravity, it creates distortions in space-time. What this makes me wonder is like, could you put this like enclose this in like a vortex and move these fast enough in a circle or vibrate them fast back and forth in order to modify gravity and like maybe put that in front of a ship, you don't actually have to expel any neutrons and you can enclose it, like create a gravity well basically as one form of propulsion.
Probably wouldn't be much gravity.
I don't think that
Really
would be.
weak.
None
mean,
of,
just-
none of my understandings of physics that is possible. I believe that you have to have a lot more energy just to distort space-time in a way in which can communicate forward impulse to something.
I
I'm
mean,
not-
general relativity allows that, but like you said, it takes a lot more mass and energy than what this system would be. So, well, you know, I guess that's the whole idea of a warp drive is, you know, generating a space-time distortion to get some kind of pulse. But I don't think I don't think this wouldn't have the high enough energy densities to make that a viable reaction. I don't think.
Okay, so
Yeah,
turning it into a form of warp drive is even less viable than throwing the neutrons out the back.
Yeah, this,
Got it.
in my opinion, this doesn't have anything to do with space-time distortions. This is just forward momentum gain by emitting neutrons mass in one direction.
I mean, maybe if you had a nuclear reactor the size of a star, then you might be able to do something cool. I don't know.
Yeah, for sure, something strange will happen then. But yeah, I thought of this as in very small size, you know, very small probe that maybe with the radio signal that you could track and see if there is any kind of acceleration. I was also thinking that if it actually accelerates near to any relativistic speeds, you will probably experience less thrust, given that there is a time dilation in the fusion process or the fission process, and you will probably get eventually less thrust as you approach higher speeds. But yeah, thank you for your consideration. If you guys want to, I have something that we can skim over quickly if you guys are interested, and it's more related to gravitational waves. It's a paper that I wrote a while ago, and that humbly, I think it has grand unification implications. If you want me to go over it 5 minutes, I can do it, or otherwise.
Yeah, I would say go for it, and you know,
Okay.
yeah, and then we'll do that quickly, and we can kind of move on from there.
Basically, this is another extreme case, borderline case that try to makes a thought experiment about technology that we don't really have yet, but that I think is within our reach in the next maybe couple of decades. This idea, I'm gonna share it in the chat, the link, if you guys want to go over it. Basically, I'm proposing that if you have in a particle collider, you have particles that are approaching each other at 99.999% the speed of light. But I'm proposing that if a space is discrete, you have actually like a classical phenomena that happens. I have this is close to more or less Wolfram's interpretation and the Wolfram's interpretation of the universe, and more or less discrete space-time properties that seem to emerge in quantum mechanics. But basically what I'm saying is that if you have two particles in a particle collider, relativistic particles approaching each other at 99.99% the speed of light, and if you are able to detect incoming gravitational waves, let's say that you know that you have detected two rotating black holes, and you know that the collision is going to happen, and you can triangulate the position, and you know that the gravitational waves are going to have a predictable direction. And I know that currently particle colliders don't work that way, but if you could align the collision of the particles in a way in which the incoming gravitational wave compresses the very last few Planck lengths before those two particles collide, you might get an extra acceleration in the interaction derived from the compression of space-time provided by the gravitational wave. So you have a compression of a space-time approaching the point of interaction, and in that very last time, say that you synchronize. It's more or less what you guys are doing with sound waves. You know, you use the sound wave and the radio frequency to position like an atom, or to facilitate the alignment and the positioning of atoms. In this case, what I'm proposing is that if you have relativistic particles, you can boost the collision with the energy provided by the gravitational wave. Because in relativity, it says that to reach the speed of light, you need infinite energy to reach that very last few millimeters per second, let's say. But if you gain that acceleration and that extra energy, instead of from adding inertia and momentum to your system by extracting it from the curvature of a space-time in that position, it's like letting a ball drop in gravity. You are doing nothing to a system, and the system is acquiring velocity because of the distortion in the space-time, because of the curvature. So if in the very extreme conditions when you only need a very tiny amount of energy to reach, this is difficult. I need time to explain it, but basically, if a space-time is discrete, there is a moment in which the two particles only have one Planck length, or whatever minimum distance unit there is in the universe between them two. If the gravitational waves facilitates, or if this also has to do with the nature of gravity. If gravity is a kind of resistance that space-time offers to inertia, and it's a gradient that objects have to follow. You curve space-time is I'm interpreting many times as a distribution in an energy gradient, where instead of a straight trajectory being the least energy demanding path, the least energy demanding path is distorted by the imposition of some kind of resistance to motion by the space-time fabric. Am I being cleared up to this point, or am I?
I think
This one's hitting the group way better, I think.
Say that again?
I think I'm picking up what you're putting down.
Yeah. Okay.
So
Go ahead.
So and just to kind of reiterate back to you, kind of in my own little simplified words, you're saying if you have two particles and you get them, you know, if you're thinking like Feynman diagram type-esque, collide them together, the relativistic mass that they're going to have at the moment that the collision is going to make a little bit of a gravitational distortion, which can kind of act sort of like a warp bubble, and give it a little bit of an extra impulse, so it can give the apparent extra impulse to get over that tachyon bubble to start acting, so you can get a faster than light, or apparent faster than light motion out of your. Is this what you're trying to do? Is get over that luminal barrier?
What I'm trying to do is trying to extract or use the energy contained or being carried by the gravitational wave, and use the collision to increase the total energy resulting from the collision. This is more like net positive energy, trying to get more than 100% of the energy that you initially put in the system, given that you spend all the required energy to accelerate the particles up to 99.9999, and then given that the collision happens in the moment in which And in the fraction, very small fraction, Planck length scale time of conditions we are talking here, if in that moment, in that point, there is a gravitational wave, like the depression or the depression, you know, the gravitational wave have like an extension of space-time in one direction and compression of space-time in the other direction, as far as I understand it. Like any other wave, you have a lower value in one point and a higher value in one point. If you use the access, one of the reasons that we actually can detect gravitational waves is because there is a contraction in the distance of the the laser has to cover, and the signals arrive quicker. That can be interpreted as well as less distance traveled in the same time. So what I'm saying is that if the two particles are going to collide, you also have some losses in the system in the collider. But let's say that you put 100 megawatts in the collision, and if the collision happens in a depression, in the moment in which the value of the gravitational wave imprints enough energy to a system as to get more than what you originally put in it. That is
have a
one way of
question.
seeing it. It's kind of a boost. You have a car and you inject compressed air into it, and you are extracting extra energy from a normal environment. So you have a flat space-time and you have a collision that happens in flat space-time. In general, well, in actuality, the particle colliders are placed in the Earth gravitational well. So you are not working in a flat space-time. So let's assume more or less ideal conditions here. You have a completely flat space-time. Let's assume in ideal conditions and then see if this could happen on Earth. But if you have a completely flat space-time and you have a collider there, it doesn't have to be a collider. It can be two relativistic particles that are going to collide with each other. I'm actually proposing that this might happen naturally around black holes, because if in black holes you have special space-time conditions, you might get events where particles can collide in a gravitationally compressed regime, and you can get these interactions that I'm proposing that might be possible.
It's like trying to steal some angular momentum from a Kerr black hole.
Say that again?
So it's kind of like trying to. So there's. Are you familiar with a Kerr black hole? The Kerr
No.
metrics, like a rotating black hole.
Rotating.
Say
So-
that, no? Yeah, go ahead.
I'm gonna butcher this, trying to do it quick. When you have a rotating black hole, the singularity is more of a torus instead of a perfect sphere. And there's something called, I think it's called the ergosphere of the Kerr black hole at this point, where it's sort of like an event horizon, but not really, where space-time itself is going around the black hole faster than the speed of light. But it's not at the event horizon yet, because it has to do with, there's a little bit of centrifugal action going on with the angular momentum of the black hole here. And so there's someone can probably find a paper and link it for me. Kerr proposes, you can send something into there, and it'll go around in an orbit, and then it can slingshot back out, and it'll have more energy in it than when you sent back out. So this kind of seems like a macroscopic analogy of that is kind of what I'm seeing here.
It could be, it's possible. More or less, the idea is that the two particles, if you have, let me draw it. You guys can see my screen, right?
You're trying to like steal some of the energy from the relativistic.
Let me show it here quickly.
You're not screen shared right now, I don't think.
No?
But
Yeah,
you should
it's
share your screen.
you might be partially there. There we go. There we go.
Do you see here my Photoshop? Can you see it?
Yep. Yep, we can see it.
Okay. So what I'm saying is let's get the cross section of the gravitational wave drawn here.
I have a quick question. So is this an external gravitational wave that's being, scattered with the two particles as well, or are you talking about gravitational waves created from the scattering of two particles?
No, gather. Let's say that you know that some black hole collision is gonna happen or something in the sky, and you can somehow orient the collision optimally to gain. It has to be, in my opinion, it has to be perfectly aligned. The direction of the collision has to be perfectly aligned with the direction of the propagation of the gravitational wave. But basically, if this
So do you
purple
have an
here,
external gravitational wave coming in addition? Is it a 3 scattering event of, you know, two, let's say you have two black holes coming in, and then you also have a gravitational wave also coming in? Is that, I'm just, fairly simple question.
say that again?
Are you scattering, are there 3 things going into this scattering process? Is there 2 particles and a gravitational wave also coming in? That's the scenario you're describing, correct?
Yes, I'm gonna try to reiterate it here more and more clearly, in a more simple way. You have particle here. This is just theoretical. It could be on a collider, and I'm proposing that this can happen on natural conditions as well. But you have this particle here, green particle here, relativistic particle, and this particle here, red particle here, relativistic as well. They are approaching each other in this direction. Let me do this more. They are approaching each other in this direction. They are going to collide here in this point. And you know that the gravitational wave is coming in this direction. So if you can synchronize the collision of the particles to take place in the moment where the gravitational wave imparts the acceleration to the particles, you will gain some extra momentum. This is my opinion. Given that these two particles are experiencing a distorted space-time that is just like if they had a little small planet pulling them together in the point of collision, you know. In flat space-time, the energy that you get resulting from the collision is 100 of the energy that those two particles have. But if the collision happens in a compressed condition, in a compressed space-time condition, I believe that the distortion of the space-time fabric conveys extra acceleration to the collision.
Yes, gravitational waves carry energy and momentum. So you can just look at this as a scattering problem with 3. You can think of the gravitational wave as just being a graviton as well, and you can model it that way. So then you could imagine it as being flat space-time with 3 particles coming in, where the third particle is a graviton, and that's a perfectly fine way to model it as well.
Nice
and
to
that
know that it could
graviton
be.
would carry
I was
energy
just
and
having a
momentum,
similar thought.
but you know, it's not going to lead to faster than light travel just because you have another thing scattering with it. But yeah, it could
No,
gain
what
energy
I'm
momentum.
not proposing faster than light travel. I'm proposing
I
that
was just drawing some
in the very last
Yeah.
fraction, if a space-time is discrete, you get to a point in which there is one Planck length or whatever minimum unit of natural space-time there is. Let's say that one Planck length is the actual resolution of space-time. If that is the case, I'm interpreting motion as the teleportation of a system from one Planck length to the immediate next Planck length. Because if space is discrete, how else can you interpret motion if not as a teleportation with the resolution of a space-time itself? You can only move forward 1 pixel of space-time if a space is discrete. If that is the case, then right before the last Planck time, before the collision, you have 1 Planck length of a space separating the two particles. If that unit of space-time is compressed by a gravitational wave, you can have something like a superposition of two particles that were not supposed to collide in that moment. It's like an anomaly, you know, because which particle, if you have like a universal clock and all the system, You don't really require universal clock. If we assume that there is a clock for this interaction, that this is a quantum system that is supposed to cohere in the future, and there are a lot of implications. You will have to know if particles are have the future information already available before the collision. If there is a universal clock and the universe happens in global refresh increments. And is that familiar? Am I communicating that idea right? If you have a universal ticking clock like a computer, and the whole universe move one step up, the whole system move one step up at the time.
You're
Like
talking
the
about
notion
the
of
wave function
computation from
universe
Wolfram.
evolves unitarily.
Say that again?
Unitary evolution of the wave function.
Oh, exactly. If you have this kind of computational evolutional steps for quantum mechanical systems, there comes a point in which the universe has to update the position of the two particles. But it has to do so without previous knowledge that the next step has been distorted by the gravitational wave. So that brings a lot of problems. This also has huge implications. The discretization of space-time. I'm proposing that is a huge problem in physics because currently you have energy information conservation, but that implies a huge problem because if you have let's say an electromagnetic wave propagating through a space-time, it comes a point in the degradation of the wave, in the scattering of the wave.
Are you familiar with Roger Penrose?
Say that again?
How familiar? Sorry, how familiar are you with Roger Penrose?
More or less everything that you can find on YouTube, like nothing, no mathematics, but more or less I know the Minkowski space-time, light cones.
You should look into his orchestrated reduction theory. What is T equals h bar divided by EG. Because I think you'll find that's kind of pertinent to some of what you were talking about.
Okay, I will go back to this and I will try to research it. Just to finish,
so what that's saying is that.
Say that again.
So basically, what that's saying is that the time until the decoherence of your wave function is dictated by the h bar divided by the gravitational self energy of the system, which sounds kind of similar to what you're talking about.
Okay. Well, I'm proposing that if space-time is discrete, it comes a point where the amplitude of a wave is smaller than the Planck length. And then after that point, you either get a complete disappearance of a wave being a gravitational wave or electromagnetic wave, and you lose that energy forever, and it's not communicated to any other point in the universe, or you either lose information because the wave keeps propagating at one Planck length of amplitude, and then you get extra energy in the universe because it will be forever amplifying without losing energy, given that the minimum energy that it can reach is one Planck length of amplitude. Not sure if I made myself clear there. Did I make myself clear?
I didn't exactly follow, but it's all good. I don't need to understand everything.
Awesome. Well, Eduardo,
basically, you have a wave dissipating, and there is a point in which the amplitude reaches one Planck length, the minimum resolution of a space, and after that point, what happens? Does the wave dissipates completely, and you cannot even see that event in the universe, or can you still see that there is a wave coming with an amplitude of one Planck length?
Depends on your model of quantum gravity.
And you lose information.
Depends on your model of quantum gravity. If you're going to invoke a Planck length, there isn't a precise consensus on the theory of quantum gravity, so it depends on the theory, I suppose.
Yeah, that was my guess, more or less. I just wanted to put the question out there because I believe that there is a huge problem right now, that if you have discrete space-time, You also have implications that not all the if a space is discrete, not all points. You cannot go in every direction because there is a limited resolution in which you can move forward. There is like an aliasing problem, like the same thing that you get in computer graphics, because you have a limited resolution, and then if you want to move 2 steps to the right and 1 step up, you can do it in different ways. Well, I don't want to keep you guys too occupied with that. More or less, I reached the point where I was interested to find out if there was any other consideration that I needed to make. But thank you for everything. Very interested in keeping close to the community.
Yeah, well,
Thank you,
yeah, and
thank you.
Eduardo or Ernesto, thank you. Thank you
Thank
as well. Okay, well, so let me do this. Let me shut down your screen share. And guys, let me see. We usually run 3 to 4 hours. It's 6:42 right now, so we've either got 20 minutes or an hour and 20 minutes left.